The most logical explanation for why aliens haven't visited humans is quite simple. Humans are too boring for them. This claim might sound absurd, but when considered carefully, it makes sense. Humanity hasn't even managed to send information faster than light yet. In this situation, it seems unlikely that an advanced civilization would find Earth worth visiting. Throughout the past year, unexplained aerial phenomena, formerly known as UFOs, have frequently made headlines. The probability that any of these phenomena are of extraterrestrial origin is very low because, as mentioned, humanity isn't interesting enough to capture aliens' attention. But what if the situation isn't like this? What if some of these aerial phenomena really are spacecraft? Then scientists need to answer this critical question. Is faster than light travel physically possible? What will be proven in this video is this. The arguments physicists present about the speed of light being insurmountable contain serious flaws and are most likely wrong. Since Einstein's special theory of relativity, the physics community has adopted this view. The speed of light is a universal limit, and no object can exceed this speed. This idea has become so entrenched that it's no longer even questioned. In high school physics classes, students are given this explanation. Accelerating an object to the speed of light requires infinite energy, therefore it's impossible. The same explanation is repeated at the university level. However, there are three major problems with this traditional explanation. These problems are so serious that they suggest the speed of light limit might not actually be a physical law, but merely an obstacle arising from the inadequacy of current understanding. Examining the details of these flaws will show how important it is to question widely accepted ideas. The first problem concerns energy, the second relates to time travel paradoxes, and the third is based on the lack of a quantum gravity theory. Analysis of these 3 points will reveal that the topic is much more complex than previously thought. The first major problem, the energy paradox, there's a surprising fact about mass that's not widely known. Most of the mass of objects encountered in daily life, chairs, phones, even the human body, isn't actually real mass. This claim might sound strange, but it's based on scientific facts. The mass of matter fundamentally comes from atomic nuclei. The nucleus consists of protons and neutrons. Each proton and neutron contains 3 quarks. Protons have 2 up quarks and 1 down quark. Neutrons have 2 down quarks and 1 up quark. Here's where the surprising part emerges. The sum of these quarks' masses is much less than the total mass of a proton or neutron. So where does the missing mass come from? The answer lies in binding energy. The energy of the strong nuclear force that holds quarks together is perceived as mass, thanks to Einstein's famous E=mc² equation. This situation means that a large portion of everyday objects, even the human body, is actually not mass, but just energy. From this perspective, considering that humans spend most of their time in front of digital screens, it could be said that this energy existence isn't being used very efficiently. The Higgs field and the reality of mass. The answer to where the real mass of fundamental particles, electrons and quarks, comes from lies hidden in the Higgs field. At this point, it's important not to confuse the Higgs field with the Higgs boson. The Higgs field can be defined as an invisible field that fills every point in the universe. This field might remind one of the 19th century ether concept, but there are 2 critical differences between them. First, The ether was thought to be necessary for light propagation. For the Higgs field, the situation is opposite. Photons, which are light particles, are massless and therefore unaffected by the Higgs field. The second difference is that while the ether was believed to behave like a fluid, the Higgs field shows the same value for all observers. The working principle of the Higgs field can be compared to a phenomenon observed in nature, like the formation of dewdrops seen on grass on spring mornings. When the air is warm, water molecules float freely in the air, but when the temperature drops at night, they condense into droplets. The Higgs field has undergone a similar process. From a technical perspective, the Higgs field has the property of being a scalar field that remains unchanged under Lorentz transformations. This property means the field is unaffected by reference frame changes. The early universe. The massless period. The events that occurred in the early periods of the universe are critically important for understanding the concept of mass. In the first moments after the Big Bang, the universe was extremely hot, and the Higgs field was not yet in a condensed state. Like water vapor freely circulating in the air, the Higgs field was also in an uncondensed state during this period. As a result of the universe's expansion and cooling, the Higgs field entered a condensation process. This condensation has now reached a state that fills the entire universe. The critical point is this. During the condensation of the Higgs field, particles gained mass for the first time. This event is called electroweak symmetry breaking in scientific literature. This temperature value is much higher than even the temperature at the center of the Sun. Here lies the critical understanding. Before this electroweak symmetry breaking event, no particles had mass. All particles were massless, and all were moving at the speed of light. Afterward, they gained mass and slowed down. It's known that the energy released during this phase transition was finite. If it had been infinite, the current universe couldn't exist, and scientific papers would definitely have been written on this subject. This situation creates a contradiction with the previously examined equation because that equation claimed that reaching the speed of light requires infinite energy. Mathematical solution and paradox. From a mathematical perspective, the situation appears quite clear. Einstein's energy equation. In this equation, the factor in the denominator approaches zero as speed approaches light speed, and consequently total energy approaches infinity. But what happens if mass also approaches zero at the same time? In this case, a zero-divided zero indeterminate situation arises, which can mathematically take a finite value. Particles in the early universe experienced exactly this process. During the condensation of the Higgs field, particles gained mass while simultaneously slowing down. This process didn't require infinite energy because the mass and velocity changes occurred simultaneously. The mathematical indeterminate situation was physically resolved. Of course, this discovery doesn't directly help humanity develop warp drive technology. Re-vaporizing the Higgs field doesn't seem technologically feasible, and such a process would vaporize the traveler as well, making it extremely risky from a health perspective. Even without being a medical doctor, it can be said that this wouldn't be a healthy method. Nevertheless, this analysis reveals that the argument that light speed is an absolute barrier isn't completely correct even from a technical standpoint. It's mathematically proven that the barrier concept isn't absolute. The time travel fallacy. The second fundamental argument physicists bring against faster-than-light travel is based on time travel paradoxes. The details of this argument work as follows. Suppose an observer named Alice watches a spaceship traveling faster than light. Another observer named Bob travels at 90% of light speed in a ship with older technology. From Bob's perspective, the spaceship appears to be moving backward in time. This situation can be visualized in a space-time diagram. The horizontal axis represents space, the vertical axis represents time. While Alice remains in a fixed position, the faster-than-light ship moves in a specific trajectory, and Bob moves in his own trajectory. Because Bob is in motion, he perceives different events as simultaneous compared to Alice. Simultaneity lines for Bob extend at different angles, and in this case, the time sequence on the ship appears reversed. A concrete example. Suppose someone on the ship drops an egg and it breaks. From Alice's perspective, first the egg falls, then it breaks. From Bob's perspective, first it breaks, then it falls. This is where the time travel paradox comes into play. If the ship really is moving backward in time as Bob sees it, Bob can give a message to the ship can take this message to the Andromeda galaxy. From there, another super-fast ship can bring the message back to Earth, and it would arrive before Bob even sent it. This scenario means Bob can send messages to the past. For example, suppose he sends himself the message, "Don't watch this video." In that case, he would never have sent the message. This logical contradiction creates a time paradox. The general relativity solution. The time travel paradox argument also contains a serious flaw. This flaw stems from the argument's reliance on special relativity theory, whereas the real universe is explained not by special relativity but by general relativity. Special relativity only deals with ideal situations where gravitational force is absent. Understanding real-world physical events requires Einstein's general theory of relativity. In special relativity, only relative velocities have physical meaning, and there's no concept of absolute zero velocity. However, the real universe is an environment filled with matter. The average velocity of all this matter can be calculated, and as a result of this calculation, absolute zero velocity can be defined. This concept is called the co-moving frame in technical literature, the reference frame that moves along with the matter in the universe. This frame carries special physical significance. Human civilization is currently not at rest in this frame. Earth orbits the Sun orbits the center of the Milky Way galaxy. The Milky Way is also moving at 300 kilometers per second toward a structure called the Great Attractor, whose nature isn't yet fully understood. If faster-than-light travel is assumed to be possible only forward in time in this special co-moving frame, time loops don't form. Whatever Bob sees, all he can do is send two signals to Andromeda, and there's nothing paradoxical about that. The question, what does the motion of matter have to do with faster-than-light travel, might come to mind. This is a very pertinent question, and the answer is probably nothing. This example was given only to show that faster-than-light travel doesn't necessarily lead to time paradoxes. The quantum gravity clue. The third and perhaps strongest reason not to trust the argument that faster-than-light travel is impossible is this. The currently known space-time theory, general relativity, is probably wrong. This claim might seem very radical, but it has solid foundations. General relativity is incompatible with quantum theory. This incompatibility leads physicists to search for a quantum gravity theory, but no successful theory has been developed yet. In quantum mechanics, the concepts of causality and locality are already turned upside down. Quantum entanglement, which Einstein described as spooky action at a distance, is just one example that challenges classical physics understanding. Similar, even more dramatic situations will emerge in quantum gravity theory. From this perspective, making definitive judgments about faster-than-light travel based on current theories might be premature. The quantum gravity theory to be developed in the future could change fundamental understandings about spacetime and causality. This situation doesn't inspire confidence that any of the current arguments about faster-than-light travel will maintain their validity in future quantum gravity theory. The history of science shows that many accepted impossibilities can be overcome during paradigm shifts. In conclusion, humanity hasn't yet been able to find ways to travel faster than light. This reality doesn't change. However, what this analysis shows is that the widely accepted reasons for why this is impossible are based on shaky foundations. The physics community needs to take the topic of faster-than-light travel more seriously. Given that current theoretical obstacles may not be as rigid as thought, allocating more resources to this research area seems logical. Perhaps if such an approach is adopted, humanity could stop being as boring as it currently is for alien civilizations. At least it could become a more interesting species on a universal scale. It's up to the reader to make a definitive judgment about the accuracy of this analysis. Are physicists really justified in their traditional approaches to this topic, or have they become victims of scientific dogmatism? Thinking about and discussing this question is valuable for scientific development. In the coming period, other widespread misconceptions in quantum mechanics will also be addressed. How the quantum uncertainty principle actually works and why Einstein's views on this matter need to be reevaluated will be examined. These topics will also provide examples that question current physics understanding,